Orbital mechanics has a way of being completely backwards, constantly defying our everyday intuition. You can easily see this in how outer planets have much longer years than inner ones, or how high-altitude satellites take longer to orbit Earth than lower ones. And that is not just because those higher orbits require traveling a longer path. The actual orbital speed up there is literally slower. The fundamental formula for orbital speed makes this inverse relationship clear. As the orbital radius increases, the velocity decreases. Yet this introduces a fascinating paradox. If you are in a low circular orbit around Earth and want to transition to a higher, slower orbit, you cannot just slow down. If you do, gravity will simply drag you down toward Earth. So even though higher orbits are slower, you actually have to speed up to get there. The secret to resolving this first paradox lies in remembering that not all orbits in space are circular. When you fire your rockets to accelerate in a low orbit, your spacecraft gains too much kinetic energy to stay in that tight circle, causing it to be flung farther out from Earth along an elliptical path. However, on the way up, the spacecraft gradually slows down like a ball thrown into the air. It is trading kinetic energy for potential energy, or speed for height. By the time it reaches the highest point of the ellipse, it has slowed down significantly and is ready to fall back toward Earth. But unlike a ball, once you are at the peak of that elliptical orbit, you can choose to fire your engines a second time to speed up again, preventing the ship from falling and locking it into a new, higher circular orbit. This two-step strategy is known as a Hohmann transfer. Even though you speed up twice to reach the higher orbit, gravity robs you of so much speed during the climb that your final orbital velocity is still slower than when you started. The second paradox is perhaps even more counterintuitive, and it comes into play when trying to rendezvous with another spacecraft. To catch up to a space station that is orbiting ahead of you in the exact same circular orbit, you have to do the most backward thing imaginable: slow down. If you follow your instinct and accelerate directly toward the station, your higher speed will immediately fling you into a higher elliptical orbit. As a result, you will end up farther away from the planet and slow down as you climb, causing you to drop further and further behind your target. To actually catch up, you must thrust in the opposite direction to slow yourself down, which drops you into a lower elliptical orbit. As you fall closer to the planet, you actually speed up, allowing you to overtake the space station from below. When you finally meet up with it at the highest point of your new ellipse, you will be in the same position, but you will be traveling slower than the station. At that moment, you perform a second rocket boost forward to match its speed and re-enter a circular orbit, perfectly positioned for docking. This strange phenomenon is reminiscent of the brachistochrone curve, where an object that falls sharply downward first can beat an object traveling in a straight line because it builds up massive speed early on. But all of this is just a small taste of how bizarre orbital mechanics can be. For instance, did you know that it actually takes less fuel to escape the solar system entirely than it does to enter a tight circular orbit near Jupiter? It sounds absolutely bonkers, and believe it or not, that isn't even the most ridiculous thing about navigating space, which we will dive into very soon.